Testive study hall. This will be the exciting second part conclusion of our geometry formulas series. If you weren't here last time, what we did is we set up an infrastructure for going over geometry formulas. So this is divided into two parts. So if you want the complete thing, you'll want to watch this session and the one that came before it. We are going to be posting the recordings of these. They're not out yet, though, but they will be shortly. And so if you missed the first one, you'll be able to go back and see it. Those of you who are on our email list, will send you an email. If you signed up to get this study hall, you'll also get that email when it comes out. This is studyhall.tested.com every Monday, 9 p.m. Eastern, 6 p.m. Pacific. And I'm the real Tom Rose. I'm one of Testive's co-founders. I'm a professional teacher, and a lot of people call me a rhombus. So make sure you don't confuse those two things. Geometry. Little bit about it. We went over this last time, but just to recap, it's 31% of all math questions. It is the second most common type of math question, so you definitely want to be hitting on all cylinders in geometry. It is the most esoteric category of math question. So to give you an example of being esoteric, requiring you to know the area of a trapezoid is particularly strange knowledge, right? It's not the kind of thing that people would just carry around because it doesn't come up a lot in day-to-day life. And the geometry section of the SAT is going to expect you to have a very specific set of formulas memorized. And the set that they choose is pretty strange. When I say esoteric, what I mean is there's this list of like 20 things that you have to know. It's not quite clear to me how they pick the things that go on the list of 20. There's equally important, interesting things not on the list, and there's plenty of things that are hardly interesting at all that are on the list. So I'm not sure how they pick that list, but you need to know this specific set of things. That's what we're going to be going over tonight, is that specific list. It is in my experience, and this is great news for any of you out there who want to improve in geometry, it is the fastest question type for math improvement, generally speaking. And part of the reason why is because of that esoteric list. So it's a double-edged sword. On the one hand, it's a list of arbitrary things that are kind of strange, which makes it more likely that you don't know some of it right out of the gate. On the other hand, what that means is there's a lot of people who don't know that stuff. So if you're willing to put in the time to memorize that list, then that puts you in a really strong position because now you're better than a whole bunch of test takers. How do you get better at geometry? Number one, make your own cheat sheet. It's really important for you to make your own sheet, not to use one from somebody else. And two, memorize all the formulas that go on that sheet. So here's a geometry process for you. Step one, complete the picture. And the idea here is all geometry problems either start out as a picture or devolve into some kind of visual representation. So it's first step, make sure you complete that representation. Often it is not uncommon for the test to sometimes give you a picture and have the picture be partially complete, and then in prose they'll give you a couple more pieces of information. You want to make sure those pieces of information are added. Next, consult relevant formulas. So examine your head, look inside your knowledge reservoir and make sure that you've got all the relevant formulas. And step three, solve the puzzle. So one of the things that is useful here is having that complete list of formulas, because what you don't want to do is spin your wheels and waste a bunch of time trying to figure out whether you know a formula. What you want to do is either be sure that you know it or sure that it's not a thing, so you're not wasting any time at all. Here's a couple of geometry dangers, things you want to watch out for. Incomplete learning. So if you don't have that list of formulas memorized, it could lead to uncertainty, and that uncertainty leads to a lot of time wasting. Similarly, thinking also leads to a lot of time wasting. So what you don't want to do is have to rederive any of these formulas, for example. Okay, so with that out of the way, that's some of your geometry basic canon. Let's take a look at some of the formulas that you'll be working on. What you want to do is put these on a cheat sheet, and everybody needs to make their own. If you were here last time and you started out, that's great. You can continue where you left off on that sheet. I bet you, and this is a running bet from last time, that both last session and this session, all the formulas that you don't know will fit on a single 8.5 by 11 sheet of paper. Worst case scenario, you'll have to use front and back. But even that, I think, is unlikely. So that should be really encouraging, that you can get all of this stuff that you need to know but don't onto a single sheet of paper, which means you should be able to memorize it fairly easily if you apply yourself. So let's dig into some of the new stuff. Special triangles. Here's a couple of special triangles. The test actually doesn't require you to know these triangles, because you can often, since these are both right triangles, right? This is 90-degree angle, and so is this one right here. Because of that, you could use the Pythagorean theorem to figure out these numbers. So you don't have to have this memorized. Pragmatically speaking, though, you do have to have it memorized, because if you end up in one of these situations, the amount of time it's going to take you to do the extra formula to get around to calculating these is going to take too long, and it's going to make these questions a bad time investment. So you want to have these ratios, and the thing to memorize here is the ratios of the sides. So if you have a 45, 45, 90 triangle, the ratio of the sides is 1 to root 2. So the longer side is root 2 times whatever the short side is. On a 30, 60, 90 triangle, the shortest side is 1. The longest side has a ratio to the shortest side of 2, so it's double. And the other leg, right, so the medium-sized side, will be root 3 times the shortest side. So in the case of both of these triangles, the ratios that I've given you are always based on the shortest side. So this is root 2 times the shortest side, root 3 times the shortest side, and 2 times the shortest side. Make sure the 45, 45, 90 doesn't have this risk because it's symmetrical. With the 30, 60, 90, make sure that you're applying the right sizes to the right side, right? So don't get the root 3 and the 1 mixed up by it, for example. You should be able to keep these straight because root 3 is bigger than 1, right? 1 squared is 1, so root 3 is bigger than 1. Can you use the Pythagorean theorem? Yasmin is asking in the chat window. Yes, you can use the Pythagorean theorem if you cannot remember these. But again, the issue here is less getting the answer correct, and it's more getting the answer correct quickly. So getting the answer correct quickly is going to mean you don't have time to use the Pythagorean theorem, and you have to be able to just pop this out immediately, which is why you want to have these ratios memorized. So let me give you an example problem. When you get the answer to this, type it into the chat window, but do not press enter, and we'll all send in our answers together. That way there will be no spoilers. I'll give you a couple of seconds to do this one on your own. Try to solve for x, the missing side. Okay, and go ahead and send your answers in. Okay, and the correct answer here is 12 root 3. It is not 24. 24 would be the length of this side here. This is 20. Go. The long side is double the shortest, so the long side will be 24. And the middle side, the one where x is, will be the short side times root 3. And remember, this is a ratio of the side to the shortest side. So that 12 is critical. Sorry, if you solved for the long one because of the arrow, that was my mistake. On these, the pattern is going to be to solve for whatever the question mark is. Or maybe I'll leave the arrow on there to throw you guys off. It'll be an extra challenge to simulate test-like conditions. I'm also going to play a high heels clicking noise in the background. Okay. The triangle inequality. Now, there are some sets of measurements that are impossible to create a triangle if they're the measurements of the sides. So take this particular triangle. It has sides A, B, and C. right? And these represent the lengths of those sides. There are some numbers that can never, there's some measures of sides that can never create a triangle. And down here I have the set of rules that must be true in order for the lengths of the sides to generate a triangle. And basically, you can remember all three of these simply as the sum of any two sides should always be bigger than the third. And it doesn't matter which two you add together, it should always be bigger than the other one. The order doesn't matter. You don't have to add the two smallest or anything like that. It's just any two should be bigger than the third. And that's called the triangle inequality. And typically the way that this is tested is by asking you verbatim, can this set of numbers create a triangle? I'll give you an example here. Again, type your answer in the chat window, but don't press enter. Okay, go ahead and send your answers in. Very good. Yes, C is impossible. And I left on the added complexity of 2 plus 1,000 is equal to 2002, or to 1002. And you might say, well, is that close enough? And the answer is no. If you recall, the way that the inequality is set up is it must be greater than, not greater than or equal to. So it has to be strictly bigger in order for this to be equal. And since we didn't have that greater than, in case C is the correct answer. And in C, if you take the shortest two and add them together, it is not bigger than the largest. All right, now similar triangles. Similar triangles are a little bit complicated for a couple reasons. One, it can be a little complicated to figure out whether triangles are similar. So the rule for similar triangles is a triangle will be similar if it has all the same angle measures. Right? So in the case of this particular triangle, these two triangles, so the two triangles are the little one here, A, B, D, and then there's the bigger one, A, C, E. Those are your two triangles. Notice that the angles, all three angles have the same measure. So they share one angle, so of course that has the same measure. But then ADB has the same angle measure as AEC, and you know that because these two lines are parallel, and you can see that the parallelism is indicated here with these little fletchings. So you know those two angles are the same because of the corresponding angles. We went over that last time. And ABC has the same angle measure as ACE. Again, for the same rule, corresponding angles on parallel lines. So you can see that these two triangles have all three angles with the exact same measure, and you always want to check that before you use any rules dealing with similar triangles. And the thing that we learn once you know that the triangles are similar is down here, and this is a little complicated to read. It's basically what it says is all of the sides should be in proportion to one another. So put another way, the ratio of AB to AC, right, should be the same as the ratio of AD to AE. So if you make a ratio with any two of the sides that are sort of the same side as far as those triangles are concerned, the ones that are in the same place, those should have the same ratio. And you can set it up with any of them. Typically on the test, they'll only ask you for one unknown, but you could do it with all three. So let me give you an example problem here. Again, type your answer in the chat window, but don't send it. Okay, go ahead and send them in. Okay, and the common answer that I'm getting is 9, which is correct. And here's how you can set this up. So first, check to make sure that the triangles are similar. These are the same set of triangles as we did in the last slide. Nothing has changed. So yes, they are similar. But always double check that. And then what we're going to do is set up the ratio of AD to AE. Right, so let's do AD to AE should be equal to the ratio of AB to AC. And I realize now that I set this up, I could have been a little bit more strategic and made this slightly simpler to calculate. But nevertheless, let's plug in as is. So AD is 4, AE is 6, and then we've got AB is 6, and AC is the unknown. What you end up with is 4AC equals 36, or AC equals 9. Now, when it comes to perimeter, the way that you calculate perimeter is the sum of the lengths of the sides of some polygon. There's not really much more to say about that other than, be ready for it when they ask you. So when I included it in here mainly for completeness sake, because sometimes they'll ask you questions about perimeter. I didn't want to leave anything out, but there's not really, much to go over. If you have a triangle and they ask about the perimeter of this, and the sides are A, B, and C, the perimeter is going to equal A plus B plus C. It's the same for any polygon. So you could have infinite sides. You could add that up. Josh, I'm not sure I understand your question. You said for the ratio, wouldn't you do x plus 6 for the extreme? For ratios, remember that you use division. I usually think of ratio as synonymous with fraction. So then you end up with all multiplication. Are you x over 6? Yeah, x over 6 would work if you did the 6 as the you did 6 and then x was the unknown. Josh, you also could set up your unknown as a portion of the total. So if you did, for example, if you called this x, or I get what you're saying. So actually, if you set x as BC, if you did the following, if you set up x was BC, like this, then your full thing AC would be equal to, so you would have in your equation, you would have AB over AB plus X. Is that what you had? And that'll work too. If you solve that, you'll get the answer. You will not get 9 for X. You'll get 3 for X. And that's because they're asking not for BC, but for AC. So you'll have to add AB, which is 6, plus the 3, and that's how you'll get the 9. So that's a little bit about perimeter. Onto area, there are several shapes where you'll want to memorize the area specifically. So starting out with, I think the most common is the triangle. You've got the base, and you've got the height. Height actually is something that confuses people about triangles. The way that you figure out the height is you draw a line from, well, you pick a side to be your base, first of all, and that takes up 2 points. Whatever the third point is, you draw a line from that point to the base and have it intersect in a right angle. That's important. Right? So from that point to the base with a right angle, the length of that line, that new line, that is your height. And that's part of the definition of the height of a triangle. You can also call it altitude. There's various letters and various names for all of these things. The important thing is that you just recognize the position on the shape, and you're able to pull that number out of there correctly. And the formula then for the triangle, once you get these sides labeled and measured correctly, is 1/2 base times height. The formula is not the hard part. The hard part for the triangle is making sure that you've picked the correct base and the correct height. Trapezoid. A trapezoid, first let's talk about the definition of a trapezoid. There's a little missing here, actually. You need to make sure that these lines are parallel for a trapezoid. You can show that a couple of different ways. But at the end of the day, you want to make sure before you use the trapezoid area that you've got parallel lines for the two bases. That's key. Otherwise, you're just dealing with a random quadrilateral, which is not a trapezoid. And the way that you calculate the area of a trapezoid is you take these two things, which are both called, for most places where you see this, they'll call both of these bases, which is a little odd. And you take base 1 plus base 2 divided by 2 times the height. I like to think of this as, you'll notice this looks like the average formula. I like to memorize this as the average of the two bases times the height. And you calculate the height the same for a trapezoid as you do from a triangle. So you pick one of the corners and you drop it down to the other base so that it intersects in a right angle, just like you do for the triangle. That's trapezoid. Parallelogram. Again, for parallelogram, you want to make sure you're dealing with one. To make a parallelogram, you have to have two sets of parallel sides. That's what it takes to be a parallelogram. And the formula for the area of a parallelogram, interestingly, is the same as a rectangle. So if you can remember the rectangle, you remember parallelogram, which is base times height. Base of a parallelogram is just the length of one of the sides. It does not go all the way over to this corner. Same thing, so for a rectangle, base times height. You calculate the height the same way we have been all along, which is you pick one of the corners and you drop a line down to the other base such that it intersects at a right angle. The square is just a subset of rectangle, although it's useful to memorize it separately, which is, if you have all sides the same length, you take any side and you square it. Same as a rectangle, base times height, although in this case it's just base squared. And then you've got the mighty circle. Circle's area is just pi r squared. Pi, or first special character, is something that you have in your calculator. It is a rational number, so it can't really be expressed except with this character. Josh, are you asking, are there other ways? Yes, there are other ways of proving that something is a parallelogram. So for example, they might give you, so Fevin, a rhombus is a subset of a parallelogram, just like a square is a subset of a rectangle. So if they ask you rhombus, you want to do base times height. Josh, to your question about are there other ways? So for all of these, there are other ways of proving that it is the shape in question. At the end of the day, what you'll need to do is prove it using the methods that I've laid out here. But so what they might do for a parallelogram is they might give you a set of lines and a set of angles. And so they won't tell you that they're parallel, but you'll be able to figure out that they're parallel by using those angles. So you'll always get back to this set of rules, right? Which is that you have parallel lines, right angles, etc. Is there a way to find the area of a rhombus using the diagonals? Yes, you can do that. That's, I think, beyond the scope of what we're going over for right now. But within the set of formulas that I've just given you, and with those two diagonals, you can figure it out. It might help you. Does it help you if I give you the hint that the intersection of those two lines will be right angles? So from that alone, you should be able to divide it into triangles. Okay, let's do it. Let's do a quick example. Okay, go ahead and send your answers in. Uh-oh, based on how many came in, I didn't leave enough time. Apologies if you got spoiled. So what is it that makes this problem take longer? You had to find the third side, exactly. Yeah, so in order to, so what type of shape is this? First of all, this is a trapezoid. Yep, and how do you know we've got two parallel sides? And this is exactly the case that you were asking about, Josh. So we didn't tell you that the sides were parallel, but you were able to figure that out because we had a 90 and a 90, right? So the only way for these two lines to exist is if they are parallel to one another, right? You can think of these as, um, if you complete the system of angles here, you know that the corresponding angles match because 90 matches 90. So these must be parallel. Now, I gave you the 5 for the height, and you had to figure out that that was the height, right? So you go to one of the corners and you drop a line down to the other base such that it intersects at a right angle. This is a special trapezoid, which is the height happens to be one of the sides. That doesn't always occur, but it happens to occur here. So the 5 was the height. But you had to figure out the length of the base down here. Now this base, so this happened to be a right triangle, so we have a 5 on one side, we have some unknown down here, and we had 13 as the hypotenuse, which I labeled on the drawing here. Now this is a special triangle, right? So you might have, if you came last time and you memorized Pythagorean triples, you might have the Pythagorean triple 5, 12, 13 memorized. If so, you were able to just pop in x equals 12 and save a bunch of time. If not, you could use Pythagorean theorem, but again, that takes longer. Then you can use the area of a trapezoid is base 1 plus base 2 divided by 2 times the height, which in this case was 8 times 12, or 8, sorry, plus 12 over 2 times 5, which equals 50. All right, now let's talk about the mighty circle. Circles are great. Why do I keep saying mighty circle? I'm not just a circle nerd. There are great things about circles. In particular, remember how with the shapes we were just calculating the areas of, all of them had many inputs. So you had to find a base and a height. Calculating the height was sometimes difficult, and it was hard to find all those numbers. Well, circles. In the case of circles, one thing to remember is that circles can be completely determined from only a single measurement. You do not need two numbers to figure out anything about a circle. You only need one. So the radius, here are a bunch of equations for circles. The equation for the area, the diameter, the circumference, and the radius, which are all labeled here on this diagram, except for the area. Area is if you shade it in. Notice that all of them can be calculated from the radius. So if you have the radius, you can get any of these circle values. Similarly, because these equations all have only one variable, if you're given any of them, you're given area, diameter, circumference, or radius, you can calculate the radius, which will therefore let you get any other one. So when it comes to circles, there's only two possible scenarios. Either you know nothing about that circle, or you know everything about that circle. There's no way to know, just the diameter but not the circumference. Knowing one tells you the other. So that's a really interesting quality of circles, and that's one of the reasons I believe that the test uses so many circles, is because it's possible for them to give you a little bit of information and for you to calculate a lot with it. Sops has a question in the chat window. Will they sometimes give you something that looks like a trapezoid, but you can't prove that it is? Yes, they will do that. But if they give you a question, it always has to have an answer. So if they ask you to say, calculate the area, there's a good chance that if it looks like a trapezoid, great chance that it is a trapezoid, because otherwise it might be almost impossible to calculate the area. So about 95% of the time, if they're asking you to calculate an area, if it looks like a shape, it is that shape. So if you're having trouble proving it, I would actually just stop worrying about it, assume that it is that shape, even though you might be wrong. You'll probably save points and time in the long run by making that assumption. How do you solve for arcs? Well, it depends on the arc. So what they're asking is, how do you solve for arcs? A similar question would be, how do I solve for a wedge? Suppose they ask me, like, what's the area of this wedge, right? The area of a wedge and the length of an arc are similar questions. And the way that you do it is it's always a percentage or a fraction of the circle as a whole. So if they were to tell you this angle, was 80 degrees or something like that, you could figure out the fraction of the complete circle. So you'd say, well, 80% or 80 degrees is what percentage of 360 degrees? And then you could figure out either the percentage of the circumference, which would give you the arc, or the percentage of the area, which would give you the wedge area. And I would list that not as a new formula, which is part of the reason why I don't have it in here, is how to calculate arcs and wedges, but rather as a way to use some of the formulas that are already in this deck and put them together in a way that allows you to calculate a new thing. So it might be that you have to combine the concept of percentages from the numbers question category with the concept of areas from geometry in order to calculate that. Yasmin, I don't know. You're giving a radius and then you have some calculated numbers, and I'm not sure if they're correct. Usually people express these in terms of pi, and they don't give the decimal. So I can't quite check you on that. Somebody else could check, though. Make sure that that's correct. Let's talk quickly about volume. Volume is pretty rare, but there are two shapes that you should memorize the volume of. Good news is they're both pretty easy to memorize. There's the box, which is much like the rectangle. It's just length times width times height. Again, every angle in here needs to be 90 degrees, much like a rectangle. And then there's the cylinder. Cylinder is basically a circle. So notice that the base of this is a circle. It doesn't look like a circle, but that's because it's drawn in perspective. But the idea here is that this base is a circle. This is called a circular cylinder. And that circle has been stretched through space to create this 3D shape. That's called an extrusion. You don't need to know that. But an extruded circle generates what they call a circular cylinder. And the way that you calculate it is you take the base times the height. And now the base of this is the area of a circle, which is pi r squared. And the height of it is h. So the volume is going to be pi r squared h. And that's how I remember it. It's just the area of a circle times the height. Right? And that's actually true of the rectangle too. You take the area of the base, which is length times width, and you extrude it by multiplying it by the third dimension, which is height. So both of these you can think of as actually almost just a slight modification to the area of a circle, or a slight modification to the area of a rectangle. All right, now the example, here's another example. Take a couple of seconds to do this one. Type your answer in the chat, but don't send it. All right, go ahead and send your answers in. It's like 16 pi is coming back. So circumference is 2 pi r, which in this case is 8 pi. Therefore, you can solve for r being 4. Area equals pi r squared, which is equal to pi times 4 squared, or 16 pi. Great. Really well done, everybody. So that was, and in just 2 short sessions there, every geometry formula that you need to have memorized. So if you were taking notes and building your cheat sheet as you went along, and keeping a record of the things that you didn't know, then you're all set and you're ready to start memorizing. For further practice, you can go to www.tested.com, where you can get free geometry problems and or work with a one-on-one 99 percentile scoring coach. Need to acknowledge a couple of people that helped put all this stuff together: Miro, Kazakov, Jackson, Havid, Noel, David, Pikachu, Chippendale, Lee, the chemist Akamando, Shonak, the closer Patel, Morella, Brazil Crespi, David, Chubby Shorts, High Song, Charles, Kitten, Smuggler, Reese, Abby, the Saint, Engelstead, Will, the Institute, Eaton, and newly added Meg, Smiles, Butler. You've been watching studyhall.testive.com, Mondays, 9 p.m. Eastern, 6 p.m. Pacific. I'm the real Tom Rose. And last but not least, if you haven't done so already, take a look at our free 30-minute coaching session, which you can set up at scheduler.testive.com. I'm putting a couple of polls out on the screen. Please help us out by filling those out before you take off. Love to hear your feedback so we can make the class better for you. Tell us what you'd like to see in the next session. And also tell us what you thought of this one. I'll be happy to hang out and answer questions in the chat if you've got any.